Hurricanes, hailstorms, tornadoes, and wildfires. These are just some of the weather hazards that displace families and disrupt lives. Many of us are familiar with the scenes of devastation these hazards cause, and the recovery process for affected communities can take months, even years. In the most extreme circumstances, some may never be whole again. This may prompt many of you to ask what's being done to reduce the risks associated with these hazards. To answer this question, the Insurance Institute for Business and Home Safety presents the Disaster Discussions podcast. Join me, your host, Rachael Penton Gauthier, as I sit down with professionals in the insurance, science, construction, and resiliency industries who help us explore the intersection of these hazards with the built environment. We'll bring you in-depth conversations with experts from across the country and highlight how science is engineering real-world solutions from home and business owners to create safer, more resilient communities. Join us for these discussions every month, and to make sure you don't miss an episode, go subscribe to the Disaster Discussions podcast on your favorite podcast app. We also invite you to engage with us on social media to ask your questions, share your thoughts, and to learn more about the IBHS mission. Welcome to the Disaster Discussions podcast, where we explore the intersection of weather and the built environment. I'm your host, Rachael Penton Gauthier, and in this month's episode, we are talking all things wildfire. We're getting you wildfire ready, in fact, as we head into a typically busy time of the year for wildfire activity. And September is also National Preparedness Month, a time to raise awareness about the importance of preparing for disasters and emergencies. And joining me today, our entire team of IBHS wildfire researchers. So we have Dr. Faraz Hedayati, lead research engineer, Dr. Srini Sanchez Monroy, research scientist, and Evan Sluter, research scientist and project engineer. So thanks for joining us today, guys.
Great to be with you.
Thank you.
Everyone joining me remotely today, and we are going to dive into all things wildfire, as I mentioned. So just to set up the background a little bit, it's already been a very busy year for wildfire. We've seen the Park Fire in California and the Stone Canyon Fire in Colorado in recent weeks. And as of this recording, the Park Fire has already burned more than 400,000 acres and is now the fourth largest wildfire in California state history. Altogether, more than 4.5 million acres have burned across the country just since January. And according to NOAA, wildfires have caused more than $81 billion in damages from 2017 to 2021. Of course, we know that number has gone up even higher here in the last few years. And now an estimated 45 million residential buildings are now in high-risk wildfire areas across the United States. And outside of California and Utah, there are no enforced statewide codes addressing wildfire exposures to residential and commercial property. So all this to say, these statistics really drive home the importance of wildfire as a research topic, and it has been quite the topic here at IBHS in 2024 so far. So first, I want to hear from each of you. First, tell me what got you interested in studying wildfire, and tell me a little bit about your backgrounds and how you came to work at IBHS.
Sure, I'll start. So I started working at IBHS during running some experiments during my PhD with Dr. Steve Coles. And at that time, I was focused on studying ember generation from different structural and vegetative fuel. And then starting 2018, he retired, and it took two people to fill his shoes, me and Dan joined IBHS. And since then, I've been working on different projects from embers, vegetation, and also more recently, wind-driven building-to-building fire spread.
I will continue. So my story is a little bit different. My background is in physics. So the first time that I started working in something related to wildfire was during my PhD. Before that, I was working on modeling sedimentation process of liquids that interaction is electrostatic, completely different. And then when I started my PhD, my advisor was trying to look for something more applied, which I agree. I was a little bit tired of theoretical stuff. And then I started working on simulation of wildfire using a CFD model that was developed by NIST. And after that, I was doing a postdoc with the wrote email at the university. He's at the U.S. Forest Service, and I was part of the University of Washington. He was collaborating with Frost and Dan at that time. So that is what I get to know IBHS, and it was really got me was that you actually can see your research translated to actions. I was looking for something more applied rather than continue theoretical work, and I found IBHS the right place to go.
And I guess finally, I studied fire protection engineering at the University of Maryland, primarily focusing on fires in the built environment and in buildings. And while I was there, I was given the opportunity to get involved in the laboratory experiments, and that led me to getting into wildfire. And from there, I had some great opportunities under Dr. Michael Gollner at University of Maryland. I got involved with the Department of Agriculture, Mark Finney, and some other big names in wildfire research, which just really piqued my interest in wildfire and this new problem that the U.S. was facing. So from there, it was always on kind of my mind, something I wanted to get back into. So when the opportunity at IBHS came up, I was excited to get back into the research space and work on this problem. So.
Yeah, I always love to hear everybody's backgrounds. Definitely a medley of backgrounds here at IBHS. And I know the three of you, an integral part of our ongoing research this year. We're going to talk more about the current project ongoing here at IBHS a little later in the episode. But first, we have to do a little history on fire. So fire spreading throughout communities, this is not a new problem. As Evan mentioned, though, it has become a bigger problem in recent years due to fires entering our built environment. But some historical urban fires, we have the London fire, the Chicago fire, Oakland Hills tunnel fire, just to name a few. These fires were all mitigated through building codes, improved fire service, and fire-resistant materials. Now, many of these same elements that led to some of those early urban conflagrations are now present in the Wildland Urban Interface. You hear a lot about that here at IBHS, the WUI, and approximately 1/3 of homes in the U.S. are now located in the WUI. So first, tell me, what is the WUI? Explain that for us, Faraz.
Sure. So the official definition of WUI is the area that the wildland meets the built environment. And it's not a line, obviously, right? It could be an inner mix, it could be an interface, but regardless of that definition, it's the area that is exposed to embers and flames from the wildland. A similar situation, like if you want to look at the hurricane site, the coastal line, right? That's where when hurricanes hit or make a landfall, that's where they hit and is exposed to the extreme case. A similar concept is applied into the fire side, where flying embers typically half a mile to a few miles in front of the fire front can land on different fuels and cause ignition in those areas. That's, to me, regardless of the official definition of the complexities of what, if it's a line, if it's an inner mix, that's what we study here at IBHS, or the area that we study at IBHS.
And we know that wildfires that enter the WUI become disasters when they turn into something called a conflagration. So tell me a little bit more about what a conflagration is. A little bit of a mouthful there. Explain the ingredients needed for one.
Yeah, so the way that building ignites in the WUI is very similar to the way that trees and other vegetation ignites in the wildland side. And thanks to the 100+ years of research that U.S. Forest Service has done on understanding of wildland fires, the concept of extreme fire behavior is well developed and studied in the wildland side. And there are a few factors that cause extreme fire behavior in the wildland. The key influencer there is rapid changes or abrupt changes in the fire intensity, which is a function of fuel connectivity and like what sources of or what fuel packages are placed close to each other, and also mass spike. This leads to not seeing efficient first responders activities in the wildland zone. A similar situation applies in the WUI, as we see when conflagration happens, the first responders activities, the influence of first responders activities are marginal in those cases. And it typically happens when we have, when homes don't have defensible space. So first responders cannot get close to protect homes, close to the fire to protect home. And also when we see dense communities, such as the one that we saw, the tragedy we saw in Lahaina. We had packed structure together, connected fuel, sheds, fences, vehicles placed between the structures, so the fire could easily change. The intensity of the fire could easily change, and fire could rapidly consume all of these fuels. That's what we call conflagration.
And what about the role of drought and wind in conflagrations?
Those definitely play an important role, as the wind provides excessive oxygen to the fire and tilts the flame. The flame basically stretch and touch the nearby fuel. And also the drought reduces the moisture content on different fuels, mostly wood fuels, and make them more susceptible to ignition.
So we know that wildfires, they're part of natural ecosystems. They've been around for thousands of years, I presume. But fast forward to the present time, and we've seen some of those more catastrophic conflagrations occur, and those are a growing problem. We know you guys have already mentioned Camp Fire, Marshall Fire, Lahaina as well in Hawaii. So talk about the growing problem of conflagration. Is it a growing problem? And talk a little bit more about some of those factors that are involved.
Sure, yeah, I can speak to that. So we're noticing more conflagrations at the same time where we're noticing an increase in the number of extreme fires. And extreme fire weather is really something that has had an uptick, where we're noticing more times during the year where there is weather conducive for this extreme fire behavior. And across the US, as we're increasing our housing density to meet the needs of homes across the US, where we're noting more densely packed communities with smaller structure separation distances between homes. And these are kind of all playing into the factors that Faraz was just discussing, where we're seeing weather that's conducive for extreme fire behavior. We're seeing the connective fuels and closely spaced structures that lead to that rapid, unmanageable fire spread from home to home that just overwhelms firefighting resources really quickly. And there's just more locations in the US where this is possible. So where we might have had an extreme fire pass through a heavily wooded area or a completely wildland area previously, now we're getting those conditions interacting with densely packed neighborhoods and have people, living in those spaces now.
Yeah, I know in one of our other perils, severe convective storms, one of the things driving losses up is that we're seeing just simply more people living in areas in the path of these storms. Very similar with wildfires. We know populations are growing still in places out west. So very interesting there, and certainly a growing problem. So I want to talk about how fires start. We have several different fire ignition mechanisms. And then, of course, we have some mitigations to help offset those things. And so I want to talk a little bit more about that. So let's talk about the three ignition mechanisms: ember exposure, direct flame contact, and radiant heat from flame. Talk about the difference between those three. What do they mean?
Yeah, if you think about any object that is burning, right? Let's say a tree or a house, and then you ask yourself, how this burning object can ignite surrounding combustibles material. So for those objects that are really close to the heat source, it is likely that the flame might be able to touch them in the right condition. If the flame touch this combustible material, they likely will ignite. That will be direct flame contact, right? Then as you move far away from the heat source, the flame won't be able to touch you, but these big, thick flames will still continue emitting radiation, which basically will elevate the temperature of the surrounding object, and they could ignite. And frequently we see these two mechanisms, radiation and direct flame contact, acting at the same time. We have seen this in the field and also in the lab experiments that we have run. Usually you have this big flame, it's gonna hit the surface, combustible gases start to be released from the surface, and then wind might tilt the flame, ignite these combustible gases, and it will ignite the other object, right? So this is like in the surrounding, the close surrounding of the burning object. But what happened far away from the heat source? So when an object is burning, it can produce embers, which are these small, hot, carbon-based particles, right? When you have a very intense fire, what happens is that create a plume that actually can loft the embers, and the wind might carry the embers miles away from the heat source. If these embers have enough energy and they land in combustible material, they will have the ability to ignite. Then you will have ignition because of embers. And what happens with wildfire is that usually you have the three mechanisms. And when you have all these embers flying across the urban area, it will start igniting different homes, and it would the problem become uncontrollable.
Yeah, and some people may know this. Some others may be surprised to know that embers are actually the leading cause of fire spread. I think one of you mentioned it earlier, they can travel up to miles away. So just talk a little bit more about this.
Sure, I'm gonna double click on what Shalini mentioned. She beautifully explained like flames versus embers. And at the initial phases of the fire, it's just small flames, right? As we see embers coming from the wildland, they go through three phases. The first one is generation, based on the wind speed, the fire intensity, different number of particles can loft from the fire, go up into the air, 200 to 300 feet. And then wind can carry them, and this is like they get into the second phase, which is transportation. And all we can do is to change the fuel bed that they can land on. We will receive embers from the wildland. And by managing that the fuel bed that the embers land on, we can protect our homes, basically. So if we provide enough fuel for the embers to ignite, the short flames can get larger and start consuming buildings, and then we are not dealing with a few feet tall flame. We are dealing with a burning home. And to Shalini's point, the flame surface gets vastly different, is much larger, and it can radiate here to the surrounding. And when we combine these two factors together, meaning the direct ignition of homes by embers, so basically embers land on the wood roof and ignite it, and the flames that started in the surrounding of the building, and then fire spread to the structure. If we combine them together, the vast majority of the homes are ignited by embers, and that's why it's very important to protect homes against embers and flame in a systematic way in two different categories.
And am I correct in thinking that once we start to see homes burned, we see additional embers created, structural embers, which can exacerbate the problem? Talk about that versus maybe an ember that comes from the wildland.
Yeah, absolutely. There is this report, I want to say it's like in the early 90s, that it says each burning home, the embers from each burning home is responsible to igniting 10 more homes. So it's like a cascading damage that happens in the WUI as the first building ignites. It can create a lot of more embers, and the structural embers, the characteristics of the structural embers are different than the ones that we see from the wildland. For example, wood-sided buildings create a lot of flat embers that are designed to fly. So as they fly off or leave the main fire, get fanned by the wind, and they get into glowing combustion as they land on the recipient fuel or different fuel beds, they go back into flaming combustion, and then it causes rapid consumption of homes in the downwind.
Yeah, and if you've ever been here to the lab, maybe to our Disaster Dynamics Academy, we actually have some 3D printed embers. It's really interesting to see the different types. Some of those structural embers are really big, and it's hard to imagine, or maybe I should say easy to imagine, one of those flaming embers landing on a home and causing even more damage. So we know that once a home ignites, there's a greater than 90% chance that it will be destroyed. So of course, the key to preventing wildfires from becoming those disasters is to to keep them from entering and spreading into the built environment. And we do this in two ways, either by hardening the structure by using fire-resistant materials or reducing the intensity of a potential fire around the structure. And we've been talking a lot about those embers. There are ways you can mitigate against those embers, and we're going to jump into more of that now. So IBHS has done the research on a lot of different elements, all the different elements of your home, from the roof to the gutters and everything in between. And those elements were used to inform our wildfire prepared home program. So I want to talk about the research insights for each of these different elements. And I want to start with probably the most talked about. They all work together as a system, but one of the most important parts of that system is that non-combustible zone 0. So I want to talk a little bit about that. Explain, what is the non-combustible zone 0?
Yeah, sure. I can take that one. So the non-combustible zone 0 is the first 5 feet surrounding the structure that we're protecting. And the reason we're so interested and focused so much on this non-combustible zone 0 is the two mechanisms you were talking about just a minute ago: hardening the structure and reducing the intensity of a potential fire around the structure. And we use those in parallel to give every home the best chance on the worst day, when it's getting that most intense fire exposure. These are the two mechanisms we have to really reduce it. And that zone 0, I guess, focuses more in a bit on reducing the intensity of a potential fire around the structure, because when we remove all combustibles from that 0 to 5 foot range, we're already giving ourselves a 5 foot buffer to reduce that intensity of that exposure. If we have an ignition or a material ignites within that 0 to 5 foot range, the mechanisms of heat transfer that Srini, or mechanisms of ignition that Srini was discussing, we're most likely going to get direct flame contact. So flames directly contacting and impinging on our structure, which is very likely going to lead to an ignition, and has really intense radiation when the flames are that close. So yeah, removing combustibles from that 0 to 5 foot range, it allows embers to accumulate in that region without igniting any larger fires, and allows them just to sit and extinguish themselves in that area.
And when we talk, sorry, Faraz, I was going to say, when we talk about combustibles, what are we talking about specifically?
So yeah, any combustible vegetation, sheds, storage, decks, anything that happens to be within the first 0 to 5 feet of the home is considered in combustibles in zone 0. And I wanted to add something to what Evan mentioned. This 0 to 5 foot is something that we are studying, but since early 90s, the problem of ember accumulation around home was acknowledged. And some codes and standard, or some researchers suggested 1 foot, some suggested 3 feet. Now we're suggesting 5 feet. So the disagreement or the struggle for enforcing this into the field is one thing, but from the scientific perspective, this problem was acknowledged since early 90s, and now we are working on the semantics of how to apply this in the field.
Right. So this 5 foot buffer zone essentially serves as a fuel break around your home. So you guys mentioned it stops those flames from getting up close to your home when it could potentially ignite a portion of your home. So this is really important part of our wildfire prepared home program. And there's another zone I want to talk about. We're going to talk more about the 0 to 5, but talk about that 0 to 30 foot radius. So let's say you've cleared everything combustible out. You've pushed it out 5 feet. What about that space between 5 feet and 30 feet? What is in that space and what isn't in that space?
So beyond zone 0, so 5 to 30 feet, is what we should is an area that most homes have to some sections of it, right? Not all homes have 30 feet surrounding them because of the limitations on the parcel size. So what the analogy that we use there is to convert tall flames into short flames and short flames into creeping flames, right? So we gradually reduce the intensity of the flame as it approaches the building. To do that, we need to sparse out different fuel packages in 5 to 30 zone. These fuel packages could be sheds, could be auxiliary dwelling units, or ornamental vegetation, trees and shrubs. We don't want to see a continuous fuel pass for small flames to use that and reach to the building. We want to sparse them out so the fire doesn't jump from one fuel to the other one easily.
Right. I know you've discussed before in your presentations on Lahaina, there were a lot of vehicles that served as fuel packages in that particular fire. And I'm sure other wildfires out there. So we want to remove anything that can serve as fuel from around your home to give your home a better chance of surviving those fires. So I do want to talk more about vegetation. And Sharini, you're really our wildfire vegetation expert here at IBHS. And this is really interesting because there are a lot of, I think, misconceptions about what you can and can't have close to your home concerning vegetation. I think a lot of people think this is green, it's irrigated, I water it every day, so it'll be fine, it won't burn. But as we know from research, that's actually not the case. So tell me a little bit about mulch, trees, shrubs, grass, even succulents. We get a lot of questions about that. You don't want any of that within the first 5 feet of your home. Is that correct?
Yeah, that's correct. So the first thing that I want to mention is that everything that is made with carbon will burn eventually under the right conditions, right? A tree, a shrub, mulch, could be pine straw, could be other type of mulch, but it will burn. So we have done some experimental tests at the IBHS with a really small ignition source, just 20 grams pine straw, an electrical igniter, and that's enough to burn a green tree. Of course, the fire behavior will change depending on the species of the tree, the moisture content of the tree. But what we also need to think, to have in mind is that when we are talking about this disaster, it's not only the tree that is burning, right? You might have a neighbor which is on flames. So you have this big wall of flames close to your home that will be radiation. It will emitting radiation to your home. And on top of that, you also have even a small shrub that might ignite because an ember. That will be just the link that is needed to create the ignition, right? As I mentioned, this radiation, what will produce, it will be combustible gases released from the surface. If you have a combustible siding, gases will be there, an ember land into the shrub, ignite the shrub, and that flame will be enough to start ignition in your home. So what you are looking for is not having, avoid having combustible material around your home, even when they look kind of green.
Yeah. So tell me about through your research, what types of plants have you found? What are most likely to burn very quickly? And then are there any species of plants or shrubs that maybe last a little longer to fire?
So to answer that question, we need to discuss what is flammability of the plants, right? So when you are trying to make recommendation, what you need to understand is how easily the plants burn. How much energy the plants release, how long it burned. And that is a really difficult question because not only the amount of species that you can find, but also the different conditions. I always make the comment that when we are running the shed burns, we build the sheds, right? We know what is inside, we know the configuration, we know the structure. With plants, we don't know. You might go buy 2 shrubs from the same species and the mass will be different. And if the mass is different, the amount of the energy that will release, it will be different. So there are some guidelines, like what type of plants they will burn more easily. If you have a very dense shrub, it will release more energy. But I think at the end, the idea is it is a combustible material. And under the right condition, it will burn, and it might be enough to lead to ignition. Usually the time that a small shrub burns is around maybe 1 minute, approximately. that 1 minute flame will be enough to ignite a siding that is already releasing combustible gases.
Yeah, it's really interesting to see. We refer to some of the plants around IBHS as little green gas cans because, as you mentioned, maybe a minute or less for some of these plants to burn up. And seeing the pine straw demonstration is really interesting. We had that at our Disaster Dynamics Academy recently, where the fuel bed of pine straw is set on fire, and when those winds are turned on, it made it to that plant. It's almost scary how quickly it burns up, a matter of seconds. So really interesting to hear about that. Tell me about grass. Can green grass catch on fire around your home?
Yeah, it can. And actually, some of the recent fires, like Lahaina and Marshall, they started as a grass fire. Then fire spread through the grass, touch some combustible material in a home, ignite the first home, and then home burn more intense, create embers, and they start to spread through the community. So yes, grass, even when it looks green, it can ignite.
All right, so that 0 to 5 non-combustible zone, very, very important part of our wildfire prepared home program. Remove all combustible materials from that first 5 feet, including vegetation. So I want to move on to the next part of the home, also very important, and that is the roof. And we know that in wildfire country, wildfire territory, it's important to have a Class A roof. So Evan, tell me what that is and how that reduces your vulnerability to wildfire.
Absolutely. Yeah. So Class A roof is determined through ASTM standard testing. And the Class A roof indicates that it is resistant to fire and heat penetration through the roof. And it's also resistant to fire spread across the roof. So an instance of a Class A roof would be, and the most common example is an asphalt shingle roof. And they're very prevalent, thankfully, and they offer pretty good protection against the wildfire exposure. An example that we saw in Lahaina commonly that was not a Class A roof that resulted in the loss of structures was a cedar shake roof. These are prone to ember ignitions and also are prone to produce a lot of embers themselves. And when you're producing embers from a roof at an elevated location, they're much more likely to spread and ignite homes in the surrounding area.
Yeah, it continues to feed into that domino effect that we've discussed. Okay, the next part of the home I want to discuss gutters, and we know that when leaves and pine needles accumulate, that can provide a place for embers to again attack your home. So talk about your recommendations for gutters that you've found through research here at IBHS.
Yeah, so to your point, Rachel, gutters are designed to catch stuff, right? This could be debris, and during a wildfire, in addition to the debris that is already there and difficult to clean up and maintain, embers land on them. So we basically put something that is very susceptible to ignition right at the edge of the roof, which can, once ignited, it can provide direct flame contact to the asphalt shingles or the fascia wall on the roof. So we recommend to use non-combustible gutters and maintain it, clean that up frequently to when embers land on it, it doesn't have anything to ignite. To the earlier point, all we can do is to manage the fuel bed that the embers can land on. And that's an effective way to do so. Something that I accidentally saw during one of my experiments was that the part of the fascia board was covered by non-combustible gutter and the other part was exposed. And the exposed part interestingly ignited and the other part did not. And when I removed the gutter, it was just clean, unburned wood, which to me is similar to the way that we cool down CPUs. We put fins on it to dissipate the heat. That acts the same thing. It's a thin metal component that easily dissipates the heat to the ambient wind, and that's an effective mechanism to protect the edge of the roof and the fascia board.
Interesting. You said, did you say that you accidentally discovered that in an experiment?
Yep. I forgot to ask the colleagues in the carpentry team to extend that the gutter to cover the whole width of the building. It was just half of it. And then interestingly, we learn something new from that.
All right. Yeah. We love a scientific accident that helps us
Yeah.
learn something. The next part of your home, I want to talk about vents, and we have some really cool video that I just love to watch that shows embers entering through vents of a home, and that's a bad thing. But we do have a method where you can prevent the embers from entering your home. So talk about your recommendations on vents.
Sure. The vents need to. So we need to maintain the current amount of ventilation to not having moisture building up in the attic area or in crawl space or other parts of the building, right? And considering that we don't want to block that passage of air, we want to protect it to allow air to exchange, but don't allow embers to come in. And back in the day, Steve Coles tested different mesh screens to different sizes, and the conclusion of that research was that it needs to be at least 1/8 of an inch to meaningfully block the ember entry to the attic. And to your point about when embers get in, it's a bad day. When firefighters see that kind of fire, it's already too late. The fire is established in the home, and there is minimal thing that they can do to change the story. So that's very important to protect the openings, all openings, windows, crawl space, and vents in the attic area against ember entry.
Yeah, we mentioned those structural embers. Those can be really big, but on the flip side, how small can an ember actually be? We know that 1 inch or finer will help kind of protect you from those embers, but some of them can be pretty tiny.
Yeah, the tiny embers don't have enough thermal or are not capable of carrying enough thermal energy to ignite something. It's way less likely that they can ignite. And even for external ignition, embers need to accumulate in areas to ignite it. It's not likely that one ember causes ignition. And when we look at it through that lens, ember accumulation going through 1/8 of an inch vent or a screen, it's less likely that we see ignition under those conditions.
All right, yeah, that's what we see in that video is just a ton of those embers just flying through some of the vents and catching the home on fire. So moving on to the next part, and this is another very important part, fences. And if you've ever been to IBHS, we do a lot of demonstrations with fences, combustible versus non-combustible. And this is all about breaking that path for the fire to reach your home. So talk about fences.
Yeah, basically it's same idea that we have discussing, right? Like have the flames far away from your building. So if you have a fence, combustible fence that is ignited, that is close to your siding, it could ignite the siding. Sorry. Or it's underneath your eave, it could ignite your eave. If it's close to your window, it could actually melt the vinyl frame, for example. The window will fail, and then flame could go into the home. So the idea is, what we recommended is having the same zone zero. If you have an attached fence to your home, that zone zero needs to be non-combustible. The rest of it could be combustible. And what you are trying to do is avoiding have direct ignition, because of direct flame contact to your home or because of the radiation. Yeah, the flames coming from the fence are not big enough to ignite the home because of radiation, but could be big enough to ignite it because of direct flame contact.
And what about when you have two fences back to back, like maybe neighboring fences in a neighborhood? How can you mitigate, or how should you mitigate against that situation?
Yeah, so you should try to avoid that, right? Because basically what you are creating is a way to accumulate debris. So if you accumulate debris, could be pine straw, could be just leaf falling from the tree. They would dry it over the time, embers will land in, and you will basically are providing more fuel to ignite this thin material, and then this will lead to ignition of the fan.
Right, we want to continue to remove those sources of fuel for embers. And I want to discuss decks now. Lots of folks have decks around their houses, and you don't want a combustible deck in that zone zero either. Talk about that.
Yeah, so decks are generally something where debris can accumulate underneath of them, and they're also susceptible to embers accumulating on top. So with a deck surface, we want to make sure to avoid ignition first and foremost. So like you suggested, working to use non-combustible materials to construct the deck, and also making sure that any debris that accumulates on or under the deck is frequently maintained. So that could look like constantly going underneath and removing those debris, or using that 1/8 inch mesh or another mesh around the exterior of the deck and enclosing that underdeck surface, just to prevent debris from accumulating underneath there. But once decks ignite, it's another instance where it's a combustible material directly up against the surface of the home, so that direct flame contact is a big risk.
All right, and eaves, another part of the home. And we know that eaves can actually trap heat from the flames as well as hot gases. So what should you do concerning eaves around your home?
Yeah, to your point, Rachel, eaves are designed in a way to basically shut off the water from the roof to the surrounding of the home to protect different parts of the building. But the side effect of that is that heat can trap there, and during a fire, accumulation of heat in that area, and specifically flame contact. So as the heat attacks that, it drives the moisture out, makes it more susceptible, and then it only needs a short flame contact to cause ignition. To avoid that, we need to enclose the eave and with non-combustible material, so we don't give the opportunity to for the short flame contact to ignite eaves.
And then walls, this is really interesting. Again, there's a lot of trends here. We're talking about those accumulating embers like other parts of the home. Embers can hit a wall, they lose their kinetic energy, and then fall to the ground and begin accumulating. And of course, you don't want embers accumulating at the bottom of your walls, because as we've learned today, that can lead to the fire, of course, spreading to your home. So talk about your research on walls, and what have you guys found? What are some of the insights from some of your research here at the lab?
Sure. So Faraz mentioned earlier when he was discussing about embers, you cannot remove the embers. You will have the embers. What you can change is the fuel bed, right? Where they are gonna land. So you always wanna have embers accumulated in the wall, like in the base of the wall. So what we are finding is that with a recommendation of 6 inches of vertical non-combustible clearance at that base of the wall, basically what you are preventing is not embers to accumulate, but you are preventing the ignition of the siren because of the accumulation of the embers.
Right. Okay. Yeah, that makes sense. As you mentioned, the embers are going to find their way to the bottom of your home, but preventing the home from actually catching on fire, that is the key part of that. So windows, just a few parts left now, your home, windows, doors, bay windows, and we're going to get to accessory buildings as well. When we do we've done some of our shed burns this year, one of the things we almost always see is those windows falling out of the buildings and breaking on the ground. So you guys have some recommendations from your research that you've done on windows. So just tell me a little bit about that.
Yeah, windows, they are vulnerable in a couple ways. So we have the instances like you were discussing where the frames soften due to the heat, and we're losing the exterior pane or a pane of the window, and that's either leading to an opening, which embers and flames can then enter the building, which is why we highly recommend multi-pane windows, which are more resilient because they provide multiple layers against this. So in case one pane fails, we have a backup. We also have that air layer in between those panes, which helps regulate temperature and prevent heat passing completely through the window. We also recommend tempered glass because that further increases the resilience to that heat and radiation. So yeah, we're really looking to maintain that exterior envelope of the building and prevent either breaking or that frame melting and resulting in openings in the building. And for us, the openings or the frames that we have performed best, I should say, in our experiments, that's not coming to my mind at the moment.
So we only tested vinyl windows, and in all cases, so basically in a high wind condition, as you mentioned, the framing softened and the wind pressure could push the frame in. Under low wind or lower winds, mostly like 25 to 30 miles an hour, we always lost the outer pane, and the building was left with the inner pane in place. And to Evan's point, that's why we require a double pane tempered glass windows in Wildfire Prepared Home program.
Yeah, it seems like each burn that we've done, it's not too long into the experiment before that outer pane comes crashing down, and everybody always likes to see that for the sake of science. I want to talk about doors as well. Flames are less likely to reach exterior doors with proper defensible space around the home, but it can still happen. Again, we can have those wind-blown embers accumulating against the base of the door. So what do you do about your door?
So, we require that in addition to the door itself, which is vulnerable to radiant heat, as Shirley mentioned, similar to walls, embers can also accumulate at the base of the door, like right above the bottom plate of the door jamb and at the bottom surface of the door. Embers can accumulate there. And another accidental discovery that Steve did back in 2015, he actually was in the building looking at embers and how embers attack the building. And then he realizes that the door jamb ignited, and terminating the test and then suppressing the fire, what we saw that the smaller embers can easily get stuck in that area, and the chimney effects happen, and the fire can slowly grow and ignite the building.
Yeah, now that's something I would never think about, is that your door jamb can ignite. Really, everything is combustible around your home if you're not mitigating against it.
Yeah, absolutely. So, a good way to address this is to look at the door and similar to all building components as a system, not necessarily the component itself, and providing a 5-foot defensible space around home, and then protecting the bottom plate of the door jamb can reduce the vulnerability of doors.
And we talked about heat being trapped under eaves, but heat could also get trapped under bay windows. Not every home has a bay window, but some do. So talk about what happens when heat becomes trapped under bay windows.
That mechanism is very similar to the way that heat traps in the eave area. So that's why we recommend to box that in, so we don't provide the opportunity for debris to accumulate before or during the fire, and then embers land them and provide direct flame contact to the bay window.
All right, and then finally, and we're going to get more into this subject here in just a minute, but accessory buildings. So we know that things like sheds and gazebos, they can ignite and, again, serve as another fuel source that could help spread that fire to your home. So talk about what we're doing to prevent that from happening, what your research has shown you here at IBHS.
We started looking at building-to-building fire spread back in 2018. And then this is a huge project, obviously. So our approach was to divide and conquer. So the first phase of the experiment was to look at auxiliary dwelling units, to sheds. And then people have different types of shed in their homes. It could be a closet size all the way to a garage size shed. So in collaboration with NIST and U.S. Forest Service in 2019, we started looking at the smaller sheds. And then for obvious research reasons, the facility that we have in Richmond, South Carolina at IBHS, we can study large flames. And in that case, you looked at a 12 by 24 by about 10 feet roof height sheds, filled that with wood cribs, about 15 6A wood cribs, ignited that, and then looked at the spacing between the source, which is the shed, and the target, which is a 30 by 4 feet footprint residential building, and different wind speed, different building components on the target. And we saw that at distances between 15 to 25 feet, depending on the heating condition and wind speed, we can have ignition on the target building. 30 feet was the shortest distance that we did not see ignition. And building on top of that, we are now expanding into testing auxiliary dwelling units at 30 feet and 40 feet separation to see the response of the target building to that kind of exposure.
Yeah, so Faraz is referencing that wind-driven building-to-building fire spread, and that has really been one of our running themes here at IBHS in 2024. So you mentioned the first phase has been completed. That was completed earlier in the spring of 2024 when you set those sheds on fire with the wood cribs inside them. We've now since moved, scaled up to a larger building, which is that accessory dwelling unit, and we are in the middle of that phase 2 right now, or actually it's just begun underway this summer. And we've already burned the first ADU. This one was filled with furniture, everything from beds, couches to accessories. And our goal, of course, is to find out the fire more about the fire behavior. Again, like you mentioned, at the different wind speeds. So I want to talk a little bit more about this project. What did you learn in phase? Well, you mentioned the structure spacing, but actually before you even got to phase 1, you had to look at several different factors. So kind of just tell me how this study got underway to begin with.
Yeah, the first step of this project was to map the flow in the research center. This is the first time that we are running full-scale experiment outside on the concrete pad rather than inside in the chamber. For obvious reasons, we don't want to risk the facility. So the first step was to understand the flow outside to see if we get a uniform enough flow to start the project. We had to move a 300 to 400 pound sensor with sensors with a heat flux with a rig around it in different locations, around 70 points for 10 different conditions, with a source, with a target, without the source and a target, all of these conditions to map the flow. And then from that, we started looking at, we built a mass loss platform to understand what is the heat release rate of these sheds. Once we gained a good understanding of that, we started adding wind to the component, to the burns. So we ignited the shed with wind with no targets. And then we started putting a target in place and then changing the distance and the relative angle of these two components.
Yeah, so to kind of put this in perspective, we set a shed on fire and turn the winds on, varying speeds. And sometimes the target building caught on fire, sometimes it did not. We see a lot of different results. So kind of just tell me more about the insights from phase 1. And if you have any insights from that first ADU burn, tell me about that.
Yeah, so the first 23 experiments, which are all of them are shed burns, we actually, as I mentioned, the shortest distance that we did not see ignition on the target building was 30 feet. And that's a recommendation that already exists in NFPA and other building codes, that 30 feet separation, which was based on modeling. Now we have experimental results to back it up. And for the ADU burns, we are starting, so the first test, we started at 30 feet separation. And we looked at the response of the target building to this exposure. Because of the different compartments that we have in the ADU, the fire doesn't grow in a exponential curve or in a uniform way. As the fire starts in the living room and then moves to the kitchen and then moves to the bedroom, the heat intensity that we receive on the target building and the way that it changes is very different from the shed burns. So I guess it's too soon to talk about the response of the target building today to a burning ADU after one burn, but maybe in the next several months we can regroup and talk about this to see, to compare the difference between ADUs and the sheds.
And I mean, do you have any particular goals in mind? Are there any particular questions that you're hoping to have an answer to by the end of this phase 2?
So there are different questions that we can answer. One is just visualizing the fire. If I want to choose one sensor to put in my experiments, that would be a camera. So we should not underestimate the impact of visualization of fire. So we can educate the public, educate the scientists by just looking at the fire and flame behavior. That's one thing. In addition to that, this would go eventually to different building codes in the US or maybe around the globe. These experiments, I don't expect to see these experiments in the near future because there's a lot of investments going into these experiments. So changing the building code is the other one. And the other goal would be influencing CAT models. Right now, we are working with some of our member companies to share the data with them so they can do some sensitivity analysis to see if they see the same trend of damage based on the different wind speeds and spacing between the source and the target. So it's a multi-layered issue that we are handling right now.
So in phase one, we learned that 30 feet is the distance that you would want a shed to be if homeowners are considering putting a shed in their backyard, or if they already have one. 30 feet really is that key distance that we found to minimize that damage or to eliminate that damage to your home. And what about phase 3? We're eventually going to be moving on. Be larger residential buildings that are about twice the size as the ADUs that we've just begun burning. So we're really scaling this experiment up over time. Talk about the purpose of that and what that phase of the experiment will look like.
Yeah, the last phase of these test campaign would be studying at fire spread from one residential building to the other. And the sheds are 10 by 12 by 24, and the ADUs are 25 by 25, so we almost doubled the size. And then the third phase would be doubling the size of the ADUs. So we are looking at a nominally 30 by 40 feet, 1.5 story residential building. And for obvious reasons, we would not have the privilege to run multiple experiments. That would be probably one or two. And I believe it would be a very, how we can close this loop is to look at those experiments at the end of these test campaigns.
And I mentioned earlier, these ADUs that we've just begun burning, they're filled with furniture, and the sheds were filled with wood cribs. Talk about why we have such a realistic home that we're setting on fire. You see this home, and it looks like a home you could move right into. Why do you guys have furniture, and why do you have it such a realistic setting for this particular experiment?
So the general idea is to have a realistic exposure as possible, right? So you want to have the right amount of fuel and the correct type of fuel as well, because you want to actually know what will be the exposure coming from a realistic building. And also, an aside project that we are working with the University of Berkeley is measuring emission. Something that is really a concern is what is the emission coming from this type of fires. So we know what is the fuel. We can measure that. We can take samples and analyze in lab experiment, the small lab experiment. But also we are collaborating with them to have to take samples of the emissions coming from these burns.
All right, now all of this will be used to inform our next big project, or one of our next big projects here at IBHS, which will be that community level work in the not just wildfire prepared home, but wildfire prepared neighborhood. And we know you guys have talked a lot about all these different components of the home working together. It's really a system, and you want that system to work at the parcel level, but you also need that system to work at the neighborhood level or the community level to really prevent these conflagrations, because you can mitigate all you want on your property, but if your neighbor has, fuel in their yard and things like that, that's not going to help the neighborhood out. So just talk about where we're headed next with our research here when we're looking at the community level and wildfire.
Sure. So as you mentioned, this is an ongoing project, right? We are basically in the phase that we are discussing how to approach this problem, but the final goal is to have some kind of program of mitigation that make reduce the vulnerability of a neighborhood. So the way that we are looking right now at the problem is, let's say, different layers. The first layer will be what you want to do is avoid the fire to enter into the community. And we have discussed the different ignition mechanisms: direct flame contact, radiation, and embers. So the first goal is analyze what is the likelihood of that neighborhood ignite because one of these ignition mechanisms. And that could be translated into look what is around this neighborhood, right? Let's analyze the type of vegetation or even other neighborhoods around it. And based on that, what are the mitigations that we need to have in order to stop the fire from entering into the community, or at least reducing the likelihood? And the next step is basically basing the idea that there is no such a thing as a fireproof neighborhood. So there is always a likelihood that the fire will enter into the community. So when and if the fire enters into the community, you want to avoid having conflagration. You want to reduce the amount of houses that will be lost. And what that means is you need to look into what is the structure separation, what is the connected field within the community, evaluate what is the risk, and define guidelines to reduce that vulnerability. And that is where all this research that we are doing plays an important role, right? All the results coming from wind-driven building-to-building fire spread, from ornamental vegetation, and from research that other institutions are doing, played an important role here.
Faraz, Evan, any thoughts on where we're headed next?
Might just echo kind of, what Srini's saying. I think all that we're doing right now is really just hopefully going to come together and help us scale up our knowledge and recommendations or programs that work to create resilient communities and really bend down the risk curve for homeowners and communities and give them some peace of mind around their preparedness for these disasters.
Yeah, I would agree with Srini and Evan. We will see wildfires in future. There is no question into that. But there is no need that we see a conflagration case such as what we saw in Lahaina or the campfire. And by investing the right resources into this problem, by experimentally from numerical simulation or CAT modeling perspective, I'm hopeful that in the next 10 to 20 years, we can understand this problem and then, again, see only sporadic damages in communities rather than losing the whole village or town.
All right. Well, thank you all for your very hard work you've put in this year. You guys are, everyone here at IBH is hardworking, but the fire team is definitely putting in overtime in 2024. So thanks for all your research. Thanks for your insights today. Very interesting subject. And we're going to hear lots more about wildfire here in the months and years to come at IBHS. And thank you for joining us today on the Disaster Discussions podcast. And we'll be back next month with a brand new episode. We'll see you then. Thanks for listening to the Disaster Discussions podcast, an IBHS production. Subscribe to our podcast on your favorite podcast app or watch the podcast on our website at ibhs.org/disaster discussions podcast and on the Insurance Institute for Business and Home Safety's YouTube channel. Connect with us on our social media pages. And for more great content from IBHS, including ongoing research efforts happening at our facility and more, visit ibhs.org.